Ferguson-Gow from the University of Reading. I'm also the chair for this session. And I'm just going to talk today about a slightly different title, but broadly the same. We're modelling non-linear rates of trait evolution across, in a heterogeneous way across trees. First of all, I just need to thank people funding me. These are my PIs. Andrew did all the heavy lifting with the coding in the back end of this, and Chris helps out too. So we know that there can be variation in the rate of evolution of a trait. If this is a time tree, it might have a particular rate parameter, but that might have increased. But an interesting way to look at that is, rather than increasing the rate parameter, you can increase the length of the tree. So these colour codes are going to be consistent throughout this talk. So orange will always refer to the time tree or the Brownian expectation of the evolution of the trait. Yellow is always going to refer to a linear rate increase. So another way that you can look at this is with some plots like this. This is just the expected change in a trait over time. You can see that this is the Brownian expectation, and here we've got a lot more variance because the rate's 3 times higher. That's the same here with the log rate on the y-axis and time on the x. Again, I have a lot of these plots in this talk. But we know already that these rates are probably heterogeneous across large trees. So in this instance, you've got your Brownian expectation. There's no change from your trait evolution is proportional to the time tree, and this clade's had a massive increase in rate. You can see that on this expected change plot. As soon as we get to the increased rate clade, there's a huge divergence in the variance of the trait. So we already know about this, and relaxing the assumption of rate homogeneity across trees has led us some really interesting things. We've got this sort of variable rates in the evolution of mammal body size. This is related to speciation rate. By relaxing the assumption of homogeneity, we can find these clades that have had exceptional speciation rates. And you can even use increasing rates to look at things like this. This is from a paper that was identifying positive phenotypic selection only from trait data and phylogenies. But in this talk, I'm really only concerned with trait evolution rather than this speciation type stuff. So these rates could also increase in a non-linear fashion. So for example, here we've got our time tree in orange, whereas in this situation here, there's been a big increase in rate near the roots of near the basal branches of this tree, but the rates near the tips have decreased. This gives you this well, it's not exponential, it's a power relationship. This gives you this decay in evolutionary rate over time relative to your Brownian motion expectation. Again, this blue colour is always going to refer to this particular type of pattern. And this is a delta pattern. So delta transforms the node heights of the tree by raising them to a power, and that power is exactly the delta parameter, in this case 0.4. You can see that on the expected change plot here, when at the root of the tree there's this massive increase in variance. Coming towards the tips, it's much more in line with the Brownian expectation, and if this was to continue, this would become smaller still. You can also see the opposite pattern when delta's higher than 1. You get a power relationship as rate increases over time. You can see the branches are compressed here and extended near the tips. And that's reflected in this expected change point here. You're seeing much less variance compared to your Brownian expectation, and that's coming more in line towards the tips. So in general, these are the various different patterns that I'm sort of talking about here. But these delta processes might also be heterogeneous amongst the tree. So here you can see this clade's experienced a delta process of lower than 1, which you could think about perhaps in some kind of radiation in trait value, whereas this one's the opposite. This is a little harder to interpret, but evolutionary rates are speeding up towards the tips. This could be something like adaptation towards niches or something like that. So we've extended the variable rates model that allows uses RJMCMC to infer the locations and magnitude of variable rates to also include these types of tree transformation parameters such as delta. It also works for things like lambda, kappa, early burst. Any transformation that can cause that changes, works on the branch lengths of the tree, works within this framework. And essentially what we're trying to do is use those transformations to stretch, compress, and in some way transform the tree so that the resulting tree is describable by a single rate parameter. So essentially trying to make the tree as Brownian as possible by transforming it. So just a few slides to show the accuracy of the model, I suppose. This is just one example. This has 400 tips, the delta of 0.4. this is a Brownian tree just simulated under a birth-death process, and I've selected this node and transformed that node by a value of 0.4, again a delta process. Then simulate some trait data with Brownian motion over this tree, put this one into the model and see what comes out. So what we have here, this is the original tree, and this is the result from the model. And what you're seeing here is the parts of the tree that are coloured are transformed according to the values of delta that are referred to be at those nodes. And I'm only looking at the values of delta that are present in the posterior over 90% of the time. So you can see it's found the correct node with a positive delta, and there's just a couple of little erroneous sections where there's some low deltas. This section of the tree is characterised by transient deltas that don't appear in the posterior enough to be considered interesting. Another way to look at this is to look at the branch lengths of the original tree that the data was simulated on versus the branch lengths of the tree that's been recovered. Obviously you'd expect a one-to-one and an orange relationship because they just haven't changed here. And you can see we're doing a pretty good job of finding the magnitude and location of deltas in this instance. And I've done this over a range of tree sizes, a range of values of delta, a range of clade sizes here, and also a range of numbers of delta processes within the tree. And as long as your tree is over around 50 tips, and these clades are bigger than 10 species, you do a fairly good job of finding and locating these deltas. So the next step really is to find, it's all well and good if these can be recovered in a simulational way, but do these processes actually occur in real data? So there's some evidence for an early burst pattern in the primates that was shown in 2010. An early burst pattern is quite similar to a delta, except the relationship between rate and time is exponential rather than a power relationship. But that, to me at least, suggested that these primates are perhaps a good target group to try and find nonlinear variation in rates of evolution of body size. So this is what I got. These are marginal likelihoods estimated by a stepping stone sampler for a Brownian motion model. The linear variable rates model, the delta model, and delta and variable rates at the same time. And we find a huge improvement over variable rates of Brownian motion when we allow these delta processes to be put into the tree. And again, it's the same colour coding scheme as before, so and the same processes as before. These are the deltas that are present in the posterior over 90% of the time. And I've transformed the original time tree by those deltas. So downward pointing arrow indicates a delta lower than 1, as does the blue. Purple is the opposite, greater than 1. So this is what these clades are. This is the New World monkeys. These are these tiny little marmoset things. Then we've got the apes here. And I think these two are particularly interesting clades because they show that you can have these nested processes. So burst and evolution at the origin of the New World monkeys, followed by burst and evolution for these really extra small marmoset type things. And you also have a nested process here, but in the opposite direction. So you've got the apes having some kind of burst or adaptive radiation of evolution here, whereas the gibbons are seeing something opposite, almost no evolution at the root of their clade, with increasing rates towards the present, and a net reduction in total evolution versus the Brownian expectation. Then there's these other clades here, the Columbini and the Guilons and Verdets. So we can look at the, I've selected the New World monkeys here just to demonstrate because they have the most extreme patterns. So this is simulated data over the portion of the tree relevant to the New World monkeys. This is the Brownian expectation, and this is what we actually see on the delta tree. There's a huge burst in the accumulation of variance of body size at the root of the clade, and that still stays high to the present. This is the expected, the log of rate against time, and with your Brownian expectation down here. These are the same plots for the other clades, so you can see there's quite considerable variation in the strength of these delta processes. In the Guilons, it's almost matched up quite nicely with the Brownian expectation, whereas the Columbini seems to be evolving much slower in body size compared to the Brownian expectation. The apes have a similar but less strong pattern compared to the New World monkeys. You can see on the apes here, here's the little resurgent section where you get gibbons. So I'll just leave this slide up. I think this shows kind of what we found in the primates and how the model works. So this is the tree that you've seen, and then here we've got rate over time, but for all of these delta processes and clades included within just one plot. So here's the Brownian expectation time, and and then you've got the newer monkeys and the gibbons here, or guenos, etc., etc. That's me done, so we've got a few minutes for questions.
So is there a prior or some form of limit on the number of shifts that the method can detect?
Yeah, so we have an exponential prior on the number of shifts you can pop in and out, but and that's completely flexible as well. But the standard is just an exponential prior. But at least within the primates and the simulation data sets, we found that it's quite robust to prior. So if we set it to have a uniform prior, we get back the same results. The only difference is when you have a more uniform or more relaxed prior, the number of transient deltas. So if I just go back to this tree here, these deltas are the ones that appear a lot of the time, and you quite often get deltas popping in and out. And the main effect of relaxing the prior is you get a lot more transient deltas, but you still manage to find the locations of the strong deltas. So it seems to be fairly robust.